We spent quite a lot of time in the lecture talking about these parallel plate capacitor systems. Typically we have one plate here and one plate here. This one will have a bunch of positive charge on it. This one will have a bunch of negative charge on it. And we have an expression that says the electric field in the interior here is the charge density on either plate divided by epsilon naught, our electric constant that we're using quite a bit here. In problem number 45, they reference a parallel plate capacitor, but instead of two planes like this, the capacitor is made up of two disks. So there'll be a disk here and a disk here. This will be loaded with positive charge right here, and this will be loaded with negative charge right here. And so there really isn't anything different you have to do to handle this thing. It's just that they're disks now, and there will be an electric field that exists between the two disks like this. And there still will be an electric field which will still depend on the charge density. In fact, all the same equations can be used to get this problem to solve out. It's just that now when you're working on this problem, they want to know what would be the potential difference between these two plates here in order to make this happen. So if you put a battery on these two disks here to get them to charge up, as diagrammed here, what would the V of the battery be? Is it a 9-volt battery, a 1.5 volt battery, or what? But the delta V of the battery would be the delta V across the plates because they're connected that way. And that's what the first part of the question is asking for here. So there's just a small manipulation of some relations we already know in order to get a working equation to do this. In particular, we know, for instance, in the case if there was a proton sitting right here, right up against the positive disk, if it went all the way across to this side here, its potential energy would change by the amount delta U is QE times, say, D, where D is the spacing between the two plates. I think we've done this a couple times in class. But we know there's a relation between the potential energy delta U and the potential V, and they're just related by this Q. So if we divide both sides of the equation by Q and by Q here, this side becomes delta V. Delta V is E times D. And this is a very important expression here when dealing with these parallel plate systems. Potential difference between the two plates is equal to electric field times the spacing between the two plates. So my D didn't come out very well, but again, it's delta V is equal to E times D, where D is the spacing between the plates. So if you just knew the electric field, which you do, when you know the spacing between the plates, which you do, this must be the delta V that was required to get it to charge up, either plate to charge up, to produce the electric field that's required then. And nextly, if you sort of know E, you can calculate sigma. So I think part B has something like it wants the Q on each plate, something like that. It wants the charge. Well, how would you find something like that? Well, you know the electric field between the plates. That was given in the problem. And you know there's a relation between the charge density and the electric field given by this expression up here that I wrote very early on in the problem, sitting right there like that. So if you know the electric field, you can find the charge density. The charge density is just epsilon naught times E. That's the charge density. How do you find the Q? Well, remember that Q is just charge density, say, times the area of either plate. And you can find that. You know it's a disk, you know the radius, and you know the area of the disk.